Awesome. So Chengpeng, thanks for joining us today. I know we have a really small group, but we're very excited to talk to you. And I'm in particular very interested in kind of the intersection of LLMs with more formal techniques such as fuzzing, which is what I'm working on, or static analysis like this, um, uh, or other unexplored areas like maybe abstract interpretation. So I'm really curious about this work. And I think you're one of the authors people have been talking about in our Slack a lot recently, which is exciting. So we're glad we're able to get you to come present. So yeah, thanks for taking some time out of a Sunday to talk to us. And with that, I'll give you the stage.
Okay, hello, hi everyone. Welcome to listen to my talk. Great thanks to Max the invitation. Let me first briefly introduce myself. So my name is Chengpeng Wang. I'm a postdoc at Purdue University right now. I just start to do some research on the language model aided static analysis because previously my PhD supervisor is very conservative to language model because they think it's always hallucinated, always cannot have some kind of example soundness guarantee. It's a very typical PR person. But right now, my current professor, host professor at Purdue, very interested in such kind of thing. Very eager to use LLM to solve some open problems in the static analysis. In this talk, I just introduced my research project. Actually, has been published in NeurIPS recently, which is about data flow analysis with existence of the language model. I will give some background about this topic because I noticed maybe some of you do not have a background about the program analysis or bug detection. Let's begin. Because we have entered, obviously, we have entered the era of artificial intelligence, generative AI. So the programming itself has been changed a lot. The programmers, no matter you are the students or the very senior developers, you do not need to write the code line by line. You can just use different kinds of generative AI bots to write the code, to generate the code. You can just write the prompts uh, for example, write comments, write some kind of requirements in natural language. This means the programming activity has been significantly changed. Uh, Writing code itself is very cheap. The more difficult thing is that we need to validate the correctness of the code, no matter whether this code is generated by AI or written by human. So in software engineering community, people try to improve the correctness or improve the reliability of the code with two typical techniques. The first one is dynamic testing. So this is very typical technique. We can just when we write our own code, we often use some inputs to check whether the outputs reach our expectation or whether this program crashed during the runtime, right? So this is very traditional technique and very intuitive. And second thing is that we can use static analysis to analyze the code. So this is not quite intuitive because maybe you are not very familiar with some static analysis technique. So I will give more introduction at the beginning of this talk. So in this talk, we just focus on static analysis. So first, I will give some background about this technique, and then I will introduce my research on the action model-aided static analysis. Basically, I will introduce this paper, LMDFA. And lastly, I will just highlight a very interesting direction, which is called neurosymbolic static analysis. Yes, maybe this be fancy word, neurosymbolic. It's very fancy concept, but actually, I think it really can really solve some own problems in the static analysis community. So at the end of the talk, I will give some brief introduction about my vision on this direction. Let me first give some background about the static analysis. Quite different from the program testing. Static analysis means we analyze the code statically, right? So in this case, we don't need any kind of input. So such techniques can give very rigorous guarantee from the perspective of mathematics. For example, whether exists any inputs such that some assertion violates in the specific program location. Or we can try to prove such statement, that is, for any input, whether a given assertion in the program always holds. So these are very essential problems in the static analysis. So after we have obtaining such answer to these questions, we can do different applications upon this program. For example, we can do the compiler optimization, right? We can delete some died code if the code never executed. And in the past several years, actually past 20 or 30 years, a very, very successful application of static analysis is the bug detection or security auditing. So let's look at this code snippet as an example. So as you can see in this code, this is a Java program, and we can find that there are several non-value, for example, as a line 10, a line 8, and a line 12, because here's the argument of this function calls just come from the input. So when user gives 0, this string, as input of this function call, the return value will be assigned to the variable c. So C can be 0. So in this case, this program actually contains the non divide by 0 bug, because we can detect such data flow paths in the program, right? Because the return value, which can be 0, can be propagated from the line 12, line 13, and back to line 1 and line 5. So this can cause a divide by 0 bug at line 5. So as long as we obtain such data flow paths, we can just conclude that this program is not safe. It has some bug. So if this code is generated by the AI or written by the human, we can use such static analysis technique to discover such bugs. So this is very, very practical solution, actually. But I have to emphasize that this problem is very difficult. I have to highlight this theoretical barrier, because Ryan theorem told me if we want to analyze any input, this input consists of the program, the Turing complete language, and the property. For example, whether this argument or whether this value is 0 or not. Such problem is undecidable. This means we cannot design a deterministic algorithm that can solve any kind of input correctly in the finite time. So in this case, we cannot always solve the problem perfectly, right? So in practice, if we want to solve the problem in finite time, to make the algorithm give the output in finite time, we have to do some kind of approximation, which means over approximation or under approximation. So these can induce false positive and false negative, which means the static analysis reports some bug. It's actually the false positive. It's not the real world bug, the real world true bugs. And also it can miss some bugs. So due to the undecidability of static analysis problem, such over approximation or under approximation can introduce such false positive and false negative. So this is a very hard problem. But I also need to point a very exciting or recall a very exciting achievement in the past 20 years. That is the SNP solver. Because previously we can just analyze the AST, the abstract syntax tree, to detect the bug. But based on the SNP solver, existing techniques can try to encode the program schematic with logical constraints. So finally, we can use solver to solve whether some property holds or not by checking the satisfiability of the constraints. So typically, there are some typical lines of the static analysis, such as symbol fusion, path-sensitive data flow analysis, and some memory safety detector, which is Facebook infer. So here, the Facebook infer is a very, very famous industrial static analysis. And they're the leader of this project actually awarded with Goldell Prize in
And
2016.
that's
So this is
the incorrectness logic one, right?
incorrectness logic. Yeah.
Yeah. Okay.
But actually in the infer, they actually model the memory states with separation logic
Right.
by
And I
adoption.
think
Yeah.
didn't Peter O'Hearn just go make another company for 3 years or something, and then he left?
Yeah. I will recall. I will
Okay.
recap these slides later.
Okay.
I just emphasize that. estimate solver, the solving-based static analysis can actually achieve a great success. But it's not enough because although there are different kind of bug detectors have been designed, research gaps here exist, and static analysis are not really deployed in the industry context as we expected because we find that existing technique requires intermediate representations. For example, if we want to analyze the C program or C++ program, we need to compile the code from the source file to the LVMIR, which is generated by Clang compiler. And if we want to analyze Java, we can use another infrastructure called Suite to generate the IR for the Java program. So based on such IR, existing standardized technique can be applied. But here, the question is, if we write the code in the IDE, the code itself is incomplete. We cannot compile it. So in this case, we cannot obtain the intermediate representation. So in this case, how to analyze the code with existing technique? Unfortunately, the answer is we cannot directly apply existing static analysis techniques. And of course, we still need to face the problem of the customizability. Let's go back to this example again. So this is a divide by zero bug, right? Very typical bug, well-defined bug. But when we analyze real-world programs, we actually need to just face different kind of third-party libraries. So in the original case, we found there is a function called, for example, the pathInt. We know that the pathInt may return the zero value, but sometimes, at least in most of times, we cannot model the semantics of the library functions. We are not aware of their semantics. So in such case, how to analyze the very typical bug types? This is the question because we cannot exhaustively enumerate their specification. So this is the first point. A second point is we still have a different kind of bugs to be detected. For example, the MISRA C is a very famous guidelines for the C programmers. And this guidebook shows a very long list of the buggy patterns. So if we want to use existing technique to detect such bugs, we have to hack the compiler internals. Because in the first point, we actually state that we have used the IR, different compiler generated IR for the analysis. So if we want to customize the bug detector, we also need to hack the compiler internal. But this is far from trivial for non-experts. So this is a very disappointing thing because although the academia have claimed that we actually achieve very good performance, precision, scalability of the static bug detector, but unfortunately in industry, not so many people really interested in static analysis. They more care about the testing or fuzzing. But the good news is we actually enter the new era. We actually have a new tools or new building blocks, which is called the large language models. So ideally, we want to take the large language model as the magic box, right? Because if we want to analyze the program, we can just feed the program and also write the question in the prompt and ask the model, LLM or GPT, could you please tell me the answer? Could you please detect the bug for my for me? Okay, of course they can give some answers. So actually, it shows a paradigm of a new forms of the static analysis. And this is not the dream because Peter O'Hohen tried to explore this direction again. Because just maybe last month or 2 months ago, he just announced that he will join Meta again. But this time, not about his project. No, it's not related to symbolic reasoning. It's just use large model or AI to do the automatic reasoning. So I feel that it would be a very promising direction in the future, no matter if industrial, but also some industrial people try to explore this direction. So this means maybe in 2008, Microsoft released the Solver V3. So it opened up the door of the automatic verification or estimate solving based static analysis. And right now, the LM can be a new building blocks for us to analyze the code, to interpret the semantics of the code. So here are brand new opportunities for us. But also, we need to face some challenges. So now I will introduce my research about the LLM-aided static analysis. So basically, I will introduce the LMDFA, which is called Language Model Aided Data Flow Analysis. So basically, static analysis is very broad area. Anything can be called as static analysis as long as it does not execute the program. For example, string matching can also be regarded as a static analysis. But here I want to formulate the scope, which is called the data flow analysis problem. So specifically, we want to examine the reachability relation of the source and sink. So here, the source means the faulty value. For example, the zero value, if we want to detect divide by zero bug. And if we want to detect, for example, some taint vulnerability, for example, cross-site scripting, the source indicates that this expression contains the sensitive user information. So this means source. And sink means the sensitive operation. For example, the divisor or some parameter or argument of some sensitive function invocation. So as long as we answer the question that whether the source can flow to the sink, we can detect such kind of bugs. So this is a very general formulation of many static bug detection problem. So actually in our work, we focus on this problem only. Okay, so how to use LLM to do such kind of detection? So actually, our basic intuition is that we can just feed the program to the LLMs and throw these problems or questions to model. So in this case, a model can really interpret the semantics line by line. For example, here they can conclude that at line 14, the value of z can be 0. So it can report this divide by 0 bug. So here is our vision. In the previous or current static analysis, we need to hack the compilers, and we need to after the program can be compiled. But right now, we can just use LLMs to do the detection. So in this case, we can analyze the code as text to data. We don't need to compile the program. And second thing is we can easily customize analysis by writing prompts. For example, we can give some few short examples. For example, the buggy cases, so that the models can really discover the bug. And more importantly, previous analysis relies on very sophisticated algorithms. For example, pointer analysis or different kind of function solving technique. But right now, we can just achieve the detection in a data-driven manner. Maybe the model do not behave well in some cases, but we can fine-tune the model. We can try to write better prompts to improve their performance. So here is our vision. We can try to explore this new paradigm of the static analysis, powered by language models instead of formal methods. But all of us have to face this problem. That is hallucination. Models can always tell you something, but you can never trust them, right? So in this case, if we ask a model a more detailed problem, for example, whether the variable z at line 13 depends on the value of variable x defined at line 10, he will give the wrong answer. So the model will give the wrong answer. This is very terrible because if we can take the output of the model as a correct one, assume they are correct, this error will be amplified if our pipeline contains different rounds of promptings. So the central issue of our work is to mitigate the hallucination, especially for the long programs and very complex debug. So let's go back to the algorithm design when we are the undergraduate students. When we want to solve a very tricky problem, very hard problem, what can we do? Actually, divide and conquer is always very general and very powerful solution, and even become the philosophy. So actually, in our problem, if we face a very long program, we can try to decompose them, right? So in this case, we can mitigate the hallucination in one dimension. And secondly, if we focus on very complex bugs, we can this bug can be detected if we validate a very complex program property. But if we can validate the property by some small parts, simple ones, actually we can also mitigate the hallucination. So this is a very high level idea. So I will give more illustration. So basically, our technical design just comes from very standard technique in the static analysis, which is called summary-based data flow analysis. So let's go back to this example again. So if we want to detect divide by zero bug, we can just start from the zero value and to see how it propagates in single function. Attention here, we only focus on single function. So in this case, we can decompose the whole program to a single each functions. So also we can obtain another summary shortcut of the data propagation from B to this return value. Okay. So in this case, we can find that this value will be propagated into this correlate function and also will be propagated out of the correlate function and back to the main function. And or eventually it will reach to this divisor. So here you can see that if you want to detect the bug, we don't need to reason the whole program in one prompt. Instead, we can just decompose it to check their data propagation in each function one by one. And assume that the model had a very good ability of understanding the shortcut snippet, and each single function typically very small. So in this case, we can mitigate the hallucination. And also, we need to check the branch condition because sometimes such propagation is not feasible because especially in this case, if zero is x is zero and b is zero, this branch condition will make the propagation from b at line 2 to the b at line 4 infeasible. So we also need to check such branch condition. So in this case, we can design an agent-centric solution, which means we can decompose the program into these three into these three sub-problems. First, we identify the source and sink. So this is the prerequisite of the bug detection, right? According to the bug definition, we can do this thing very straightforward. And secondly, we can summarize the data flow for each function. So here we can just retrieve the function according to their call graph. And also finally can candidate the data flow summaries and obtain the data flow paths. So eventually we can just validate the feasibility of this path, right? So for each problem, it's not so difficult. It just focus on the shortcut snippet or very relevant values in the program instead of the whole program. Okay, but it's the such decomposition alone actually not enough because if we want to extract, for example, if we want to extract the source and things, of course we can use structure model to extract them. But to further mitigate the hallucination, we realize that it is actually the structure search. Mostly it's a structure search problem. So we want to leverage the structure model to synthesize such a script to identify the source and things. For example, we can just provide this prompt template and write this example code. So actually, this is very traditional programming by example problem. And we can use structure model to synthesize a script program to identify all the sources and sinks in this example program. So based on the program by example schema, we can finally obtain the source extractor and sink extractor. and apply these two kind of extractors to the whole code base to detect the bug. Sorry, not detect bug, to extract the sorting things, right? And of course, it is just a one-time effort, right? So if we use LM to identify the certain things, if we have the huge code base, it's very expensive. But as long as we synthesize such extractors, the result can be reused. Extractor can be reused. So this is one-time effort can make us to just spend a very low token cost on this. So on the second part, of course, we actually need to use LM to interpret the code semantics to see whether this value 0 can propagate it to specific value in another program location. So here we actually introduce a few short share of thought design because we actually need to coach the model, coach the LM, how this value can be propagated. So in a few short examples, we will just give some propagation patterns, for example, passing by argument, passing by parameter, and something like that, and also the indirect flow through pointer operations. So finally, in this case, the model can just discover the propagation from the line 8 to line 12 and finally reach the line 14. And lastly, I just want to validate the correctness or self-satisfiability of the branch condition. So similar to the first stage, we can just ask the models to check whether this path is feasible or not, this path condition is satisfiable or not. But instead, we just feed the pass information to large model and ask a model to encode the pass condition. For example, in this code, if we want to see whether the propagation from the line 2 to the line 4 is feasible or not, we can just feed this information to the large model. And of course, we should assume that the variable b should be 0 because we just focus on such 0 value propagation. And in this case, the solver can deterministically check, okay, this is unsatisfied satisfied logic constraints. So we can safely prune these superior data flows. So very similar to the first stage, we used tools to solve the problem. So here is the workflow of our work. So we decompose the problem. So this is one key design to mitigate the hallucination. And second thing is that we introduce the tool using. Actually, we synthesize the new tools because this script is the tools we use. But this tool is not exist. We actually synthesize such tool to help us to extract certain things. And also, such script help us to determine whether this path condition is satisfiable or not. So this is also created by the models. And also, in the second stage, we use few-shot chain-of-thought prompting strategy to interpret the code semantics in single functions. Okay, so here is the main result of our work. So here is the evaluation upon the Julia test suite, which is very typical benchmark for the static analysis. And you can see that we evaluate an approach upon these four lecture models. And for the overall detection performance, we can find that the precision required very high. We can find that precision of the divide by zero bug is a bit lower because it requires the path sensitivity. It requires the checking of the branch condition. So the LM can still hallucinate in some cases because the synthesized Python script encoding the path condition are not always correct. And we compare approach with three baselines. The code queries industrial tools it supports compilation free and customizable analysis, but writing such query is quite difficult. Actually, if we want to customize the detector, we have to write over 100 lines of domain-specific queries. So this is not easy for the developers or users. And Pinpoint is the very famous. I'm not sure whether it's famous internationally, but at least it's very famous in mainland China. This work is published in PLDI 2018 and is commercialized. And this tool is actually very scalable architecture and can support million lines of code just in 14 or half an hour. And end-to-end detection means we just detect the bug by prompting. Okay, so you can see that our approach can achieve comparable performance than with Pinpoint, but our approach is compilation free. Analyze the code even if the code is not complete. And we'll also do the ablation study because at the beginning I say problem decomposition is not always solve the problem because we still need to mitigate the hallucination for each part. So here the ablation study means that we just if we do not use do not synthesize the extractor and we just directly use model to identify the source and sinks, we'll find okay the performance will degrade significantly. And also for the other two ablations, we can observe the similar phenomena. So here is the takeaway. So LDFA, you can regard it as an agent because it has tool using and it can actually, we have the memory design because previously we just have the program and then we extract the source and sinks in the memory and then we extract the summary in the memory, pass in the memory, and finally we can just determine the path condition feasibility. So we have the basic design in agent perspective, but it is not strictly be regarded as agent because we do not have the planning ability, right? Because the whole workflow is determined by ourselves according to our domain knowledge on the static analysis, data flow analysis. So someone called it as the agentless because the agent without the planning ability is agentless. So I think it's maybe for the program analysis problem, I'm not sure whether it is possible to use a general reasoning model or agents to solve it. Because if we can really solve it and use LLM to plan a new solution, I think it's the outcome would be a new standardized algorithm, right? But right now, I don't think the model can have such intelligence level to do this. So I think our domain knowledge of this standardized problem are also very important if we want to solve it, even with selection models. So finally, I will give more further generalize our work in LMDFA. So you can regard it LMDFA as an instance of neurosymbolic approach because we do not want to solve the problem in a neural way because if we solve it in a neural manner, hallucination is very terrible. So we need to mitigate the hallucination by reducing some neural analysis to the symbolic analysis. So here, the key design is the program synthesize. We use the LLM to synthesize the program to create the tools, to use the tools. So this is a very interesting thing. And second thing is that we use LLM to do the thematic interpretation. So in each single functions, we can just analyze the code using LLMs. And let's further summarize the rules we used in the LMDFA. So basically in LMDFA, we use the model as a code interpreter to summarize the semantics of each function, right? And more importantly, it is we can analyze incomplete program and also the programs in other programming languages. So this is also very natural extension of the LMDFA. And the second role is the program synthesizer. It can achieve the program reduction to achieve the original program, to solve original program by synthesizing some domain-specific tools, to use some experts tools to solve it. And lastly, I also want to further discuss another rule of the language model, which is called knowledge base, because sometimes, as I mentioned before, we need to customize the bug detector, right? And sometimes we cannot get a specification of some library functions, but importantly, we can use the LMs to get such specification because model itself is a very good knowledge base, right? It has been pre-trained on such kind of data. And even for some bug types, some bugs are very difficult to formulate. We can even ask the model to give some buggy examples. And then we can leverage such examples and some existing, for example, code cloning detection to find the similar code, buggy code in the code base. So this is also one possible way to leverage such model for the static analysis. So as a whole, we can just design or instantiate the neurosymbolic analysis following how the human analyze the code. Because as a human, we have the left brain, we have the right brain, and these two kind of brain actually analyze or solve the problem in two totally different ways. First, the left-hand brain conducts a rigorous reasoning. It's very similar to the traditional program analysis, right? To analyze the code line by line. But sometimes, actually most of the times, if we write the code, we only analyze the code line by line, focus on the code we write instead of the library functions. Because for some library paths, we actually analyze it or just get the semantics according to the function name. This means if we are the first year undergraduate student, I do not have experience. So I have to go to the details. But after practice, I have the experience, I have knowledge. So the right half brain actually store many pre-knowledge, important knowledge to conduct intuitive thinking. So in this case, we can just analyze the code, short code snippet very quickly according to our intuition. And also for the knowledge, some important programming knowledges, we can also retrieve our knowledge from our right half brain. So the problem is how to instantiate a framework, the neurosymbolic standards framework for the specific problem. So here I just demonstrate a very interesting instance for the data flow analysis, but maybe for the program repair or fuzzing or testing, different kind of testing, we can also follow the similar design. And lastly, I want to still mention the OpenAI o1 because this is always the problem. We have to discuss it, right? So here I just mentioned it as large reasoning model because it is not the mechanism is totally different from the next token prediction, which is key mechanism of the large language model. So for the large reasoning model, I have the comparison with o1. Although our paper is published, but it still has one experiment on it. We actually have the one experiment on the real-world program, real-world Android malware program in TenBench. But this TenBench actually offers the ground truth of the TenFlow. But here we found that if we focus on each file, and such file may contain over hundreds and maybe thousands lines of code, we found that OpenAI o1 will hallucinate if the size or the number of the program lines exist, for example, 700. So which means within this scope, or the program is not quite large, it can very effectively detect the bug, very precise with no false negative. But when the program very long, actually current version still hallucinates, even predicts the wrong line number. So as you can see, if we use GPT 3.5, it's very actually maybe the basic model, the very the weakest model right now. We can achieve the comparable, even better performance than OpenAI for our problem. For our problem, this is the key point for our problem because I think the o1 is a general purpose reasoning model. It's not customized for our problem. So in the direction, I think it is we still have some work to do. Even if we are industry, we do not have the resource, computational resource. We are not access the high quality data, but we can still use some small model, relatively small model, to design an agent solution, agent-centric solution, so that this solution just specific for a very domain-specific problem. So the last reasoning model, O1, O2, or O10, may be effective generally, but it might not have a good performance, even if it has the same precision recall to some extent, but maybe it's very expensive. So this means we still have our research still has a value. And also, we can leverage some existing statistics data to do the planning, to coach the model. For example, to based on the reinforcement learning, we can get a better planner to analyze the huge code base. And last year needs to emphasize that the hallucination is a central problem. No matter how powerful the model is, we cannot totally trust the model outputs. So here, maybe we can use some better prompting strategies, right? For example, channel start is a good way to mitigate the hallucination when we want to solve some reasoning problem. And also tool using is a very interesting and promising way to mitigate hallucination. So for different problems, different domains, we have different expert tools. So this is very important. And lastly, if we want to interpret the semantics with such models, we need to do the semantic alignment. At least for current models, I still find that it cannot align with execution semantic or program semantics perfectly. So currently, it's still a very important problem. So here is the code of my paper, MDFA, and also I'm maintaining paper repo about the language model for code. So this is a very basic version, just to have around no more than 200 papers. But I'm still working on right now. I actually extract about 600 papers from 20 venues in the conference. For example, the conference of software engineering, programming language, security, machine learning, and NLP, something like that. So basically, I collect 20 or 21, 22 or 23 venues and collect all the papers about language model for code. So I will update it and categorize it because I'm trying to categorize these papers use language models. And I think it could benefit the community and focus on their interest better. And it will be actively updated. Okay, that's all for my sharing. I'm very glad to take any questions.
That was super interesting. Thank you, Shengpeng. Could you elaborate a little bit on the synthesis step? Like I've found that LLMs sometimes struggle to write regexes or to write AST parsing logic. So I'm curious what your experiences were with getting LLMs to synthesize something that could connect to source and sink. That seems pretty tricky to me.
Yeah. Because I didn't mention this detail here. So as you can see, this code snippet, the shadow shows the one that's by the program by the LM. So basically, we actually provide the skeletons and some
Oh,
feature
okay.
example there. So this is very important. Otherwise, I think the model cannot really
Yeah.
understand
It,
how to use three features. Yeah, it's different. It's
yeah, that's smart.
impossible.
I
Yeah.
don't
So
think the
because
models are very good at parsing yet, like at making parsers. I mean, they're good at reading code and interpreting it, but they're not very good at like writing a parser for code because there's all these edge cases they don't think of.
I see. Yeah, because the parsing library, for example, tree is very domain specific.
Yeah.
I think the
Yeah.
model cannot, and actually the tree has different programming languages support
Right.
and had different versions. So even as a developer, as a human, I cannot really figure out very
Yeah.
smoothly sometimes. So yeah, it's a problem. And also another thing I want to share about is that I noticed that Microsoft has this project to design a model-friendly language.
Right.
For example,
Interesting.
the office. So if we use the PowerPoint, we want to beautify this slides, right?
Yeah.
So they actually design the user-friendly language, and it can invoke some atomic instruction to
Mm.
manipulate these slides. But basically, this DSL is model-friendly, which means it's very close to the natural language. So the model can just synthesize such program in this DSL very
Yeah.
easily, according to future examples. So similarly here, we just provide some just give the prompts, gives the templates. So the model just needs to write yeah, even if they do not have the source code of the specific library, they can still imagine that, okay, this is a pen, this is a node type, is ASD node type. So I think it's somewhat model friendly. Yeah.
Ankit and I are both avid users of the interactive theorem prover ACL2, which is based on Lisp. And I think that the models will probably never be good at ACL2 for the incredibly stupid reason that they would need to count the number of closing parentheses, which
Okay.
they actually can't do, right? Because the models, like sometimes a token might have two parentheses, sometimes it might have one parenthesis. The
Yeah, yeah.
token size to, there's not a bijection, right? Like between token size and number of characters in ASCII. And so as a result, it's going to routinely miscount the number of parentheses, which means that really you would want a DSL that it captures that with entabulation rather than with parentheses. Right. So there's all these like funny ways that languages that work for humans are going to turn out to be tricky for LLMs. And I think we're going to be
Yeah.
reckoning with that over the next few years.
Yeah, exactly. Yeah.
Yeah, even
So,
for synthesis, I was recently writing Lisp, using Lisp uh, to write a parser for org formats, and I was using the help of ChatGPT. So asked it to like write a subsection of it, and it was generating something, and it was always having the parents problem. And I was saying, I don't want parents problem. Just make sure that there is no parents issue and the
okay.
Yeah.
parentheses are balanced, but it was still always producing those errors. Like it had to be done manually.
Yeah.
Yes,
It's,
yeah. I feel that. Yeah, especially when I try to use, for example, try to write because I write static analysis based on sorry,
yeah.
LLVM because yeah, if I write the LLVM path, yeah, I still encounter similar problems. Yeah, but basically, I think the model, yeah, finally, maybe current model even has a better ability because it can maybe have the REPL level understanding. It will analyze other parts of your whole project,
Yeah.
and such ability will make the model better adapted to your context. So I think it cannot solve the problem, of course, I think. But it can generate some skeleton. We can change it a little bit. And
Yeah.
during this interaction, maybe the model will be better. I hope so. Yeah.
I think that there's a killer product to be made that I'm not going to make because it's outside of the wheelhouse of my company around interpreting logs using LLMs and then surfacing useful information, telling people like, here's the part of your code that seems the most relevant to the crash that was in
Yeah,
this
yeah, 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 yeah,
log,
yeah, yeah,
that
yeah,
type of
yeah,
thing,
yeah.
right? And somebody's going to
Yeah,
do
I
it in the
think
next
yeah,
year or
it's
two.
very yeah. I think the yeah, this is related to another important. I think it's my dream actually. Because someone always asks what is static analysis, and
Mhm.
someone say, okay, this is code search. Whether the code search is static analysis or not, or
Right.
whether this log analysis is static analysis or not. So I think from the perspective of PL community, it's definitely not the traditional or typical static analysis. But I think from the perspective of problem domain, I think eventually the ultimate shape of the static analysis is just the code QA system.
Mhm.
We can ask them something, no matter in natural language or in some kind of query, we can get some facts from the code base. And we do, as long as this process do not involve the execution, the direct execution, we can just regard it as a static analysis.
Yeah.
So I think maybe you mentioned the log. I think it's very important to design. For example, um, how to establish the connection or traceability between
Yeah.
the log and the code, and
Yeah.
how to conduct a multimodal analysis.
Right.
So yeah,
No,
I
I
think it's
think
very
you want structured logs and you want to know what line of code in your code base every line of log comes from.
yeah
And then
yeah
you
yeah
can
yeah
imagine like a perplexity type interface to interact with your logs, see what happened, and get suggestions for how to fix it, right? And
Yeah, yeah,
that's like
yeah.
very clear cut. I think that probably there's going to be a Y Combinator or other startup company that does this in the next year or two. And then as soon as it's done, every logging company like BetterStack, um, Datadog, all of them will make their equivalent, and it'll be a commoditized product. Like there's going to be a million people doing essentially the same thing because it's not that hard to do the basic product, but it's like a very high ROI thing to have. But yeah, I think it's a super interesting area. And there's cool FM stuff to be done too, right? Like if you start thinking about, if you think of logs as traces, well, then obviously there's connections between traces and the semantics of the program. And now you can start looking at like what invariants hold over your traces and stuff like that, and then trying to connect it back to, the language model and that interaction. So I think there's some really, really cool, problems to be explored to your point now that we have this new tool in our toolbook.
Yeah, yeah, yeah. Because currently, I think the IDE do not have the good support of debugging. If the
Right.
it just yeah jump between the code instead of the non-code materials. So
Yeah.
I think yeah, yeah, yeah. Material the log is just one very typical example.
Yeah, absolutely.
Yeah.
Another thing I've encountered, I wonder what your perspective is on this from academia. So, like, we did a lot of software testing for our product using open source repos on GitHub, just testing on other people's repos. And then we
Mhm.
started getting customers. Now we have like 100 companies using our product. And the distribution of problems from real companies is completely different from the distribution of problems we found when we were testing on repos on GitHub. And so that was surprising to me. Like, I thought that we could do the academic thing and build off, problems we found evaluating on open source libraries. But the open source
No,
libraries, they don't connect to
yeah,
services.
open source libraries means that because testing is a very complex thing because
Yeah,
in academia we only focus on subject testing subject. This is our evaluation subject.
right,
But in the industry context, we need to consider different factors.
right.
Yeah, so I know there is another very interesting direction called the DBMS, database management system testing.
Okay.
Many people work on this and can find many bugs, no matter it's the open source database or closed source. But in the industry, I think one of my friends working in the database unit, and he told me actually they prefer the random testing. They do not want to config
Hmm.
the existing data MS files in
Right.
their industry context because sometimes you require some privilege. You do not have permission. You need to access some kind of data. You need to do
Yeah,
some operations, but you do not have some permission right immediately.
that's really interesting.
Yeah, so this is why I think the language model, for example, for the static analysis, someone wants to compile the code, but basically you may do not have the opportunity of compiling
Right.
such code in the IR. Yeah.
Yeah. Yeah, that's really
And
interesting.
and also I also mentioned there is the one tool maybe I just go through very quickly. So this is a tool commercialized by my PhD supervisor, the Pinpoint. This is published, the original academic paper was published in PLDI 2018. So when they opened this startup, they actually need to recruit someone to deploy this static analyzer because some industry people want to customize the detectors, but they don't know how to write the code. And also, the company can only give the release the binary code to for the commercial use. So the company, startup company, has to educate some staff to write the customized checkers to fit to meet the requirement of the partner. Yeah, but it's not easy. Yeah.
We should probably wrap up. I guess a good final question to end with is, what are you excited to work on next? What's next on the plate for, Xingpeng?
You mean what's the next step for me?
Yeah, like, is there an open problem you're really excited about, or some direction you're exploring that you're willing to kind of
Yeah,
allude
currently
to?
I want to build up a more general framework driven by language model. Actually, I have a prototype right now, but it's a bit restrictive and the scalability is not good enough. But basically, I want to design, CodeQL, right? Do you know CodeQL?
I don't.
Actually, it's just this one, CML. It's compiled by the Microsoft. And
Oh, okay.
CodeQL is their product, core product. And actually, you can just search online code is code. QL
Yeah.
is query language. And
Okay.
actually, this is very famous. Actually, maybe security expert very like it. Although it
Okay.
can not as precise as Facebook or Pinpoint, but it's very relatively user-friendly to
Yeah.
customize for customization. So the security expert can just write their own checker. It's very good, right? But such a product can only analyze the whole code base. So if we want to analyze the small ones to detect the bug, to do a more direct analysis, actually it is wasteful to run the analysis behind the whole project. And also, that work, the code QL is still compilation based. So if
Mm.
we want to analyze the product during the development time, it is not possible. So right now, I want to make to propose a neurosymbolic framework so
Cool.
that we can just interpret the semantics with selection model, but also use parsing because parsing does not require the complete program,
Mm.
the compilation, right? So
Right.
in this case, I want to organize all of this stuff in the relations, very similar to data log.
Yeah.
And data log engine is actually the very core backend of the code QL. So basically, I want to propose something like compilation-free code QL.
That's really
But
cool.
here we just use selection model to interpret the semantics instead of to write some data log rules
Yeah.
for example, to derive the pointer facts or data flow facts.
That's super cool. That sounds really exciting.
Yeah, so this is
Well,
my current goal, but basically my long term or my dream is to make the static analysis more general, more
uh,
user friendly, something like the code question answering system, and somewhat similar to what you do right now.
awesome. Well, Chengpeng, thank you so much for coming to talk to us. This is really cool. Is it okay if we post this recording on our channel so other people can watch it? Okay.
Of course, yeah.
Awesome. And if people want to reach out to you with questions, I imagine they should just email you with your email on your website, right? That's the best way to get in contact.
Okay, sure.
Okay. Awesome.
Okay,
Okay.
okay, awesome. Thank you.
Thank you.
Okay, thank
Okay.
you,
Talk to you later.
Alex. 好，
See you.
拜
Bye.
拜。